So we've made it. This is the last unit in this course. And this is finally, after all this time, this is what we've truly been working toward. We've been working toward a point where we can understand the RSA encryption system. And here we are, we can do it now. So this is very important. RSA is really, it was the first public key encryption scheme ever published, and it's still the gold standard. It is the role model for all other public encryption schemes. It is the basis for many encryption systems that are still used today, especially in commercial applications. So we need to spend some time understanding this material. You will need this if you go forward in more cybersecurity coursework. So you are free to download all these files and keep them for future reference if you like. I hope they're useful. So let's talk about today just what RSA is and how it operates. So RSA is a public key system just like ElGamal. So every user has their own customized public encryption key. And that encryption key is known to the whole wide world. Anybody can use it, even Eve. But every user also has a private decryption key that only they possess and no one else should know about. Okay? So before we talk about how we create RSA keys, let's first talk about what are messages under RSA and how do you encrypt and decrypt in RSA. Okay? So let's suppose that Alice has established already her own RSA key. The public portion of the key consists of 2 bits, okay? There is a modulus n that she works in and what's called an encryption exponent e. So she publishes 2 things, the modulus that she works in and her encryption exponent little e, okay? Her private key, the thing that she will never tell anybody ever, consists of a single decryption exponent called d, okay? We'll talk about later how these are created, and then we'll talk about even later why they are created the way they are, okay? So when Alice announces that she is going to work mod n, so that's part of her public knowledge, right? Then she can receive any plain text and ciphertext message that is an integer mod n, okay? So if she works mod n, that's her entire batch of messages, okay? 0 through n minus 1. So if Alice announces, for instance, that she's working mod 65, all right, then you can encrypt any message you wanted to from 0 to 64 and send the ciphertext to Alice. So if you work mod 65, then your messages can be any number from 0 to 64. Okay. Now a big warning here that we got to talk about in the next couple of lectures is Alice cannot use any modulus n that she cares about and any exponents e and d that she wants to choose. Only certain n's and e's and d's are allowed. Otherwise, this will not work. If you don't use n and e and d according to the RSA recipe, then successful decryption will not occur. All right, when Alice decrypts Bob's message, she will not get the original plain text. So you got to do it right, okay? So here's how encryption and decryption occur. So Alice has announced her public key N and E. So that's her modulus, and that's her encryption exponent that anybody can use, okay? So Bob wants to send a plain text message M to Alice, where M is mod N, right? So 0 to N minus 1. So since this is a public key system, Bob has to use Alice's key data since the message is going to Alice, right? Alice is the recipient of the message. So that's whose key data you use, okay? So how does Bob encrypt M? Okay, what he does is he looks up Alice's public key, right? And he sees that her encryption exponent is E. So he uses that E as an exponent on the message. So he takes his message M, he does M to the E'th power, he reduces that mod N, and that's the ciphertext. Okay, so it's very simple. C is M to the E mod N. Okay, so then Bob tells Alice that the ciphertext is little c. Right? So here's how Alice decrypts. She knows her own private decryption exponent, little d, right? But no one else knows that. And she decrypts by the same process. She takes the ciphertext message, raises it to the d power, right? That's her private key power, reduces mod N, and it turns out, if you set up RSA correctly, there is a miracle of mathematics that occurs, which I'll explain later, which says C to the D will always be the original message. So she can successfully decrypt as long as she set up RSA correctly, okay? So the point of this handout is exactly to learn how to set up RSA correctly. It's going to be a little bit hard to follow and you're not going to really understand why it works, but don't worry about it yet. The why this works, that will come later, okay? Right now, I just want to focus on how you do it. So first, let's just give an example of this sort of message exchange, okay? So here's an example. Suppose that Alice publishes her RSA key data, the public part, of course, this way. So she tells everybody that N is 8777 and that E is 23. Her private decryption key, which she hides from everybody in the world, is D, which is 8207. And trust me that this is set up correctly. It is. I triple checked it before I wrote this up. Okay, so Bob wants to take the message 4250, which is an allowable message when you work mod 8777. Right? So Bob takes the message 4250 and he's going to encrypt it to Alice. Okay, so if he's going to encrypt 4250, he looks up her key data and he knows she's working mod 8777. So he sets his modular calculator to 8777. And then he knows to encrypt 4250, he takes 4250 to the 23rd power, the message to the encryption power. Message 4250 to the encryption exponent, 23. And he, of course, reduces mod 8777 by using his calculator. And when he punches that in to his calculator, he gets 6603, and that's the ciphertext. Okay? So then Bob tells Alice, hey, Alice, the ciphertext is 6603. Then Alice can decrypt by taking the ciphertext 6603 and raising it to her secret power that nobody else on the planet knows. So only Alice can decrypt. And if you do 6603 to the 8207, guess what you get? You get 4250, and that's exactly Bob's original message. So it works. So the more you play with this, the more you're going to be amazed that this sort of round of encryption and decryption always produces the original message. Okay. It's also amazing that nobody else can do what Alice did, that somehow you can't get D from all this public information. You still can't figure out what D is if you're Eve, the eavesdropper. Okay. So I really believe that it is worth just staring at this example a lot until you really appreciate what happened and how it works. Try your own encryptions and decryptions. Make up your own messages and encrypt them and decrypt them, and just check that it always works. And it's not clear why it's secure, and it's not clear how to create keys, and there's a lot of good questions here. It's not clear why it's secure at all, and we'll do that over the next week or two. So for the first two exercises on the Canvas quiz, I just want you to try an encryption, be Bob and encrypt under that same key as above, and then be Alice and then decrypt a received message just like I did above, and just make sure you can do this. And then we'll take a break, and in the next part of this handout, we'll look at how you generate RSA keys.